Let's dive into space. Number 10. The STS-48 objects. On September 15th, 1991, at approximately 20:30 Greenwich Mean Time, a camera mounted in the cargo bay of Space Shuttle Discovery was pointing toward Earth's darkened horizon. The shuttle was flying over the Indian Ocean on mission STS-48, and as far as anyone knew, there was nothing unusual about the view. Then something moved. The footage shows a small, luminous object drifting slowly across the frame. This kind of thing happens in space. Ice crystals, debris, and insulation fragments routinely accompany shuttles in orbit, catching sunlight and appearing as drifting specks on camera. NASA engineers were familiar with all of it, and they had a name for it: space dandruff. It was ordinary, explainable, unremarkable. What happened next was not. A flash of light appeared near the lower portion of the screen, close to the Earth's horizon. The moment it did, the slow drifting object changed direction sharply and accelerated away from the frame. Then a streak of light moved through the region the object had just vacated. Independent physicists Mark Carlotto in 1999 and Lon Fleming in 2003 each published formal analyses concluding that the object's trajectory was inconsistent with ice particles pushed by a thruster plume. NASA's official explanation holds that the directional change was caused by the shuttle's reaction control system firing at that exact moment, pushing nearby ice particles away from the craft. Former NASA engineer James Oberg, who worked at Mission Control, has consistently argued this position. The timing, he maintains, is coincidence. The RCS logs from that specific window, however, have never been made publicly available, despite decades of Freedom of Information requests. 34 years later, the original uncompressed data tapes remain unreleased. If the answer really is ice and thruster exhaust, what exactly is in the footage that hasn't been shown? Number 9. The Apollo 10 music. In May 1969, 3 NASA astronauts became the farthest humans from Earth in recorded history, a staggering 220,820 nautical miles away. Commander Thomas Stafford, Command Module Pilot John Young, and Lunar Module Pilot Eugene Cernan were orbiting the Moon on Apollo 10, the final dress rehearsal before Neil Armstrong's landing. For approximately 1 hour, as they passed behind the Moon, all radio contact with Earth went silent. Then their equipment started playing music. The Apollo 10 mission was a precise technical exercise. The crew had trained for years. They knew every sound their spacecraft made, every hum of the environmental systems, every creak of metal under temperature stress. These were not nervous rookies hearing things in the dark. They were elite test pilots operating at the absolute edge of human capability, and they had been in space before. Unexpected sounds were something they were trained to diagnose immediately. What they heard defied their training. A strange, high-pitched whistling sound came through the radio communication system while the 2 modules were briefly separated. "You hear that? That whistling sound?" Cernan asked. "That sure is weird music." The sound lasted for roughly 60 minutes. More remarkable than what they heard is what they decided to do about it. The crew discussed whether to report it to NASA and concluded they should not, reasoning that any sign of psychological instability could end their careers permanently. NASA's official explanation, offered decades later, is that the sound resulted from radio interference between the VHF systems of the separated lunar module and command module. Space historian Andrew Chaikin supports this interpretation. Transcripts of the event were technically available at the National Archives from 1973, though the audio wasn't digitized and widely accessible until 2012. Apollo 15 astronaut Al Worden publicly rejected the radio interference explanation, stating the crew was far too experienced to mistake routine equipment noise for something worth concealing. 3 of the most rigorous human beings ever selected for a government program heard something they didn't recognize, agreed not to tell anyone, and went back to work. They knew every sound their spacecraft made. What was the one sound they didn't? Number 8. The STS-75 tether swarm. On February 25, 1996, Space Shuttle Columbia deployed a 12-mile conducting cable into low Earth orbit as part of an Italian-American experiment called the Tethered Satellite System Reflight, or TSS-1R. The cable carried approximately 3,500 volts relative to the orbiter and was designed to generate electricity by cutting through Earth's magnetic field. The experiment failed when the tether snapped unexpectedly, the satellite drifting away into orbit. The cameras kept recording. What appeared around the broken cable has been argued about ever since. The tether failure itself was understood and documented. Pinhole flaws in the Teflon insulation allowed trapped air to bubble out into the ionosphere, converting instantly into plasma that short-circuited the system and burned through the cable. NASA convened a mission failure investigation board, completed a full analysis, and closed the investigation. The tether was gone. The experiment was over. There was no reason for anything unusual to appear in the subsequent footage. And yet the footage shows dozens of luminous, disc-shaped objects moving near and, according to multiple independent analysts, apparently behind the drifting tether. This is the central dispute. If the objects are out-of-focus ice particles close to the camera, as NASA maintains, they cannot pass behind a cable 12 miles away. Some analysts insist the depth relationship is clear. Veteran astronaut Story Musgrave, reviewing the footage years later, said simply, "I cannot explain it." NASA's explanation invokes bokeh, the optical effect produced when a camera lens renders out-of-focus points of light as large, disc-shaped blurs. Astronaut Franklin Chang Diaz, who was aboard the mission, described the bright spots as debris that flies with us, illuminated by the sun. A routine water dump had occurred just before the experiment, producing exactly the kind of small ice particles that would catch sunlight and appear on camera. Photo analyst Mark D'Antonio initially called the objects intelligently constructed vehicles, before later attributing the effect to optical artifacts. The original mission telemetry has never been cross-referenced against the footage in a publicly available analysis. The objects that appeared around the broken tether remain, in the technical sense of the word, unidentified. Number 7. The Pioneer Anomaly. In the early 1980s, navigators at NASA's Jet Propulsion Laboratory in Pasadena, California, were reviewing trajectory data from Pioneer 10 and Pioneer 11, the most precisely tracked spacecraft in history. Both probes, launched in 1972 and 1973 respectively, were heading out of the solar system. The math governing their trajectories was well established. Everything should have been predictable. Something was wrong. Both probes were decelerating slightly more than all known forces could account for. The discrepancy was tiny, an anomalous sunward acceleration of 8.74 plus or minus 1.3, 3 times 10 to the negative 10th meters per second squared, but it was consistent, measurable, and identical in both spacecraft traveling in opposite directions. When JPL physicist John Anderson and his team formally published the anomaly in 1998 in Physical Review Letters, the scientific community treated it as a possible crack in the foundations of gravity itself. Some researchers noted that the anomaly's numerical value was eerily close to the rate of the universe's expansion. Others proposed dark matter, dark energy, and modifications to Einstein's general relativity. Nearly 1,000 academic papers were written about it over the following 2 decades. The resolution, when it finally came in 2012, required a team led by Slava Turishev at JPL to spend years reconstructing the entire mission history of both probes from archival data found in deteriorating magnetic tapes, some of which were located in boxes, stored under a staircase at JPL and on their way to being destroyed. The cause turned out to be asymmetric thermal radiation. Heat from the spacecraft's plutonium generators, which produced approximately 2,500 joules of thermal energy per second, was escaping unevenly from one side of the craft and creating a tiny but measurable recoil force. The anomaly was solved, but it took 30 years, a data rescue operation, and the most detailed thermal modeling in spaceflight history to do it. And in those 30 years, the Pioneer data was the best observational evidence in the solar system for new physics. It wasn't new physics. It was heat. The universe spent 3 decades looking like it was broken, and the answer was sitting under a staircase. The question that remains is not about Pioneer. It's about how many other anomalies are still waiting for someone to look. Number 6. The flyby anomaly. On December 8th, 1990, NASA's Galileo spacecraft swung around Earth to pick up gravitational speed on its way to Jupiter. Physicists had calculated the exact velocity change the maneuver should produce. Every variable was accounted for: Earth's mass, the trajectory, the spacecraft's weight, the geometry of the flyby. When Galileo emerged from the encounter, it was traveling 3.92 millimeters per second, faster than the equations predicted. That number is so small, it seems irrelevant. It isn't. A gravitational assist, sometimes called a slingshot maneuver, is one of the most mathematically reliable operations in spaceflight. The physics governing it are among the best tested in all of science. Newtonian mechanics and general relativity together should account for every fraction of the velocity change. Engineers bet spacecraft trajectories, mission timelines, and billions of dollars on these calculations. The math works. It has always worked, except when it doesn't. NASA's Near spacecraft, during its Earth flyby on January 23, 1998, arrived 13.46 millimeters per second faster than predicted. ESA's Rosetta spacecraft gained an excess 1.82 millimeters per second during its March 4, 2005 flyby. John Anderson, the same JPL physicist who first formally documented the Pioneer anomaly, identified the pattern and published a predictive formula in Physical Review Letters in 2008. His formula uses the latitude of a spacecraft's entry and exit vectors to calculate the size of the expected anomaly. The formula works, but no one has identified the physical mechanism behind it. Some flybys show no anomaly at all. Messenger, on its way to Mercury, passed Earth in 2005 without any unexplained velocity change. No single variable reliably predicts whether the effect will appear, which makes it nearly impossible to test deliberately. Proposed explanations include dark matter in Earth's vicinity, modifications to known gravitational theory, and coupling between the spacecraft's spin and Earth's rotation. None has produced consensus. A formula exists that predicts a force that physics cannot explain. That is not a solved problem described in polite language. That is a hole in our understanding of gravity, still open, still waiting. Number 5. The Mars methane pulses. In 2004, scientists using ground-based observatories detected methane in the atmosphere of Mars. This should have been impossible. Mars has no known active volcanoes, no plate tectonics, and no confirmed geological processes that produce methane on Earth-like timescales. On a planet bathed in ultraviolet radiation, methane breaks down within a few hundred years at most. For methane to exist at all in the Martian atmosphere, something must be producing it continuously. The question of what has been generating controversy and quiet institutional discomfort ever since. NASA's Curiosity rover, which landed in Gale Crater in August 2012, began detecting a background level of approximately 0.7 parts per billion of methane from its earliest measurements. Scientists worked to understand whether the source was geological, chemical, or something more provocative. Then, on June 19, 2019, Curiosity measured a methane concentration of 21 parts per billion, 30 times above background and the highest reading ever recorded on Mars. The mission team described it as breaking the instrument's expected detection range. The reading was real. The source was not identified. What makes the methane problem genuinely unsettling is its behavior over time. The concentration rises in Martian summer and falls in winter, following a seasonal pattern. On Earth, the most common source of intermittent, seasonally varying methane production is biology. Methanogenic bacteria, microorganisms that produce methane as a metabolic byproduct, are widespread in Earth's subsurface environments and follow exactly this kind of temperature-driven cycle. This is not proof, but it is the profile. The European Space Agency's Trace Gas Orbiter, which was specifically designed and launched to map Martian methane from orbit, detected essentially zero methane during its 2019 observations. At the same time, Curiosity was measuring its record spike on the surface. This contradiction remains unresolved. Current hypotheses include localized geological sources, subsurface chemical reactions with water, and biological production in protected subsurface environments. NASA has reached no formal conclusion on the source, despite more than 20 years of data. Something on Mars is exhaling methane in seasonal cycles, in quantities our best orbital instrument cannot detect from above. We have sent no mission specifically designed to determine whether that source is rock or something that breathes. Number 4. The Sidonia formations. On July 25, 1976, Viking 1's orbiter was photographing potential landing sites on Mars when it captured image frame 35A72, covering a region called Sidonia Mensae. Among the terrain features in that image was a formation approximately 2.6 kilometers long that bore a striking resemblance to a humanoid face, with what appeared to be eyes, a nose, and a mouth visible in the lighting conditions of that particular pass. NASA researcher Tobias Owen identified it in the data, and it was released to the public at a press conference with the description, "a trick of light and shadow." That was the official position. Then, NASA went back to photograph it again. The agency's initial dismissal made scientific sense. Low-resolution imagery combined with oblique lighting creates pareidolia constantly, and the human brain is specifically wired to find faces in ambiguous shapes. One mesa resembling a face in a region full of mesas is statistically unremarkable. The Viking image was 47 meters per pixel, with shadow filling significant portions of the formation. There was no reason, on the evidence of a single photograph, to treat Sidonia as anything other than geology. But in 1988, researcher Mark Carlotto published a fractal dimension analysis of the Sidonia formation in the journal Applied Optics, finding its bilateral symmetry statistically significant compared to the surrounding terrain. Researchers Vincent DiPietro and Gregory Molinar had also identified a second prominent feature in the same region, a five-sided pyramidal formation now called the D and M pyramid, with internal angles that some researchers argued exceeded natural probability. The clustering of geometrically distinctive features within a limited geographic area was harder to dismiss than a single mesa. NASA returned to Sidonia with Mars Global Surveyor in April 1998, imaging the formation at a resolution of roughly 4 meters per pixel. The face resolved into an eroded mesa with no artificial features, visible to most planetary scientists. ESA's Mars Express provided stereo imaging in 2006. NASA's Mars Reconnaissance Orbiter photographed the region again with its HiRISE camera. 4 separate spacecraft. 5 decades of returns to the same coordinates on a planet we have studied continuously since the 1970s. No peer-reviewed geological study has formally explained the symmetric arrangement of multiple anomalous formations clustered together in the Sidonia plain. The face is almost certainly rock. The number of times NASA has gone back to check is a different kind of data. Number 3. The Voyager interstellar wall. On August 25, 2012, NASA's Voyager 1 spacecraft crossed a boundary that no human-made object had ever crossed before. After 35 years of travel, the probe passed through the heliopause, the point where the sun's solar wind gives way to the pressure of interstellar space, and became the first human artifact in the space between the stars. Scientists had been building models of this boundary for decades. They had predictions. When the data came back, it didn't quite match them. NASA waited 13 months before announcing the crossing had occurred. The delay existed because the measurements were confusing. Voyager 1's plasma spectrometer had stopped working in 1980, leaving scientists to infer plasma conditions indirectly. The magnetic field at the boundary didn't change direction, as most models predicted it should. Only when a solar storm that erupted in March 2012 sent a shockwave out to Voyager's location 13 months later, making the surrounding plasma vibrate at a measurable frequency, could scientists confirm what had happened. Don Gurnett at the University of Iowa, who led the plasma wave science team, described the moment of realization as one where they literally jumped out of their seats. What they confirmed was not entirely what they expected. The interstellar magnetic field, measured by Voyager 1, came in at approximately 5 microgauss, roughly twice the predicted value. Voyager 2, which crossed the heliopause on November 5, 2018, at a distance of about 119 astronomical units, measured an even stronger field of around 7 microgauss. The plasma density outside the boundary was 40 to 80 times denser than in the outer heliosphere, toward the high end of predictions. And between 2013 and 2015, as Voyager 1 moved deeper into interstellar space, the local electron density increased by a factor of roughly 40. In 2021, Stella Ocker, a doctoral student at Cornell University, published a paper in Nature Astronomy reporting the detection of a faint, persistent plasma wave emission in Voyager 1's data that had been present continuously since 2017. The interstellar medium was not silent. It was humming. Ocker's analysis suggested the space between the stars was far more electromagnetically active than models had assumed. The boundary of our solar system has a magnetic wall twice as strong as predicted, and the space beyond it generates a continuous electromagnetic hum with no identified source. Something has always been pressing against the edge of what we call home. Number 2, the perchlorate revelation. In August 2008, NASA's Phoenix lander, sitting in the northern plains of Mars, called Vastitas Borealis, made a discovery that most of the public never heard about, but that quietly restructured 50 years of Mars science. Phoenix detected perchlorate in the Martian soil at a concentration of approximately 0.5%. Perchlorate is a powerful oxidizing compound. On its own, this was interesting chemistry. Combined with what NASA had already found in 1976, it was something close to an indictment. The Viking landers of 1976 carried 4 biological experiments, but the one that mattered most was the gas chromatograph mass spectrometer, the GCMS, operated by principal investigator Dr. Klaus Biemann of MIT. The GCMS heated soil samples to between 500 and 630 degrees Celsius to drive off any organic compounds for analysis. It found none. No organics meant no life. This was the scientific community's primary justification for concluding that the Viking labeled release experiments' positive metabolic results were caused by chemistry, not biology. The GCMS was considered the definitive instrument. Its negative result closed the case, except that perchlorate, when heated above roughly 200 degrees Celsius, oxidizes and destroys organic compounds. The GCMS was heating its samples to more than twice that temperature. In 2010, NASA astrobiologist Rafael Navarro Gonzalez published research showing that perchlorate combined with organic material produces methyl chloride and chloromethane when heated. Both of those compounds were detected by Viking's GCMS in 1976 and dismissed at the time as instrument contamination from cleaning solvents used before launch. The instrument that was used to disprove the presence of organics on Mars was almost certainly destroying the organics it was designed to detect. In October 2025, a team of researchers, including Stephen Benner, published a formal e-letter to the journal Science, directly challenging Klaus Biemann's 1976 conclusions, and arguing that the GCMS results, properly interpreted, are consistent with the presence of organic material in Martian soil. The paper that had served as the scientific foundation for 50 years of Mars is lifeless had potentially been wrong since the day it was published. This is not a fringe argument from outside the scientific mainstream. These are NASA-affiliated researchers, publishing in peer-reviewed literature, systematically dismantling the evidence that caused the world to stop looking for life on Mars. And still, no metabolic life detection instrument has been sent to the surface of Mars since 1976. Number 1. The Viking labeled release. On July 30th, 1976, a small instrument sitting in the rust-colored soil near Mars Chrysoplanitia returned its first result. The labeled release experiment, designed by Dr. Gilbert Levin of Biospherics Incorporated and co-investigator Dr. Patricia Ann Strott of the National Institutes of Health, worked by moistening a soil sample with a nutrient solution tagged with radioactive carbon-14. If microorganisms were present and metabolized the nutrients, they would exhale radioactive carbon dioxide. The instrument would detect it. On July 30th, it detected it. A few weeks later, Viking 2 landed 4,000 miles away in Utopia, Planitia, and ran the same test. It detected it too. The labeled release experiment was not designed carelessly. Levin had been developing it since 1956, and NASA selected it in 1970 after nearly a decade of refinement. Before launch, the team tested it on soils from Antarctica, Death Valley, the Salton Sea Flats, and White Mountain above the timberline. It returned positive results for every soil containing life and negative results for every sterile control. It had been validated thousands of times. When both Viking landers returned the same positive metabolic signal from two separate sites on another planet, the biological team gathered to consider what they were looking at. I looked at it and said, "Oh my God, it's positive," Strott recalled decades later. The scientific community's response was to point to the GCMS, which found no organics, and conclude that a chemical oxidant in the soil, not biology, had mimicked metabolism. This conclusion was not unreasonable, given the data available in 1976. What it produced, however, was a half-century of institutional certainty. No follow-up metabolic experiment was designed. No second Viking was sent. Subsequent missions focused on geology, water history, and atmospheric chemistry. The question the labeled release had asked, and possibly answered, was set aside. When Levin continued arguing that the experiment had detected life, he was treated as a crank by much of the community whose careers had been built on the opposite conclusion. Then came Phoenix in 2008, perchlorate in 2010, Navarro Gonzalez's reanalysis, and finally the Benner team's 2025 challenge to Beeman's original GCMS paper. Each new piece of evidence moved in the same direction. The chemical that destroyed the GCMS results was present at Viking's landing sites. The contamination byproducts were consistent with organic material being oxidized, not cleaning solvents. The LR results had been replicated at two sites separated by 4,000 miles, under controlled conditions, with validated methodology. Levin published a formal scientific opinion in Scientific American in October 2019 at 97 years of age, stating that the experiment detected living organisms on Mars. He died in 2021, still waiting for a follow-up mission. We sent a life detection experiment to Mars in 1976. It returned a positive result from two separate locations on another world. We decided it was wrong, built no instrument to check, and spent the next 50 years studying the rocks. Whatever was metabolizing those nutrients in the Martian soil, we gave it one test, looked away, and never went back. If you want to see more videos like this, click the video on screen now and make sure to subscribe.